In this video, we'll learn how to determine a unit cell, start a data collection, and face index a crystal. Once the crystal is centered, the next step is to collect a small amount of data in order to determine the unit cell. To do this, click the Evaluate tab on the left and then Determine Unit Cell. We'll work our way through the steps in the Manual Mode box on the right. First step is Collect Data. The exposure time and image width can be adjusted here. Click Collect to begin. We're looking for a few things on our diffraction images: good intensity across the whole frame, well-separated spots, and no streaking or doubling of spots. The first few frames here look good. To check that we're getting good resolution data, click the circle button in the toolbar. You can then click in the red area to see how far out the diffraction is going. Remember, we want 0.83 angstrom resolution or better. This crystal with 10-second exposures is diffracting strongly, well past 0.83. So to speed up the unit cell collection, I'm going to abort this one and change the exposure time to 5 seconds and then begin the collection again. You can see that there is still strong diffraction even at 5 seconds. In many cases, you may find you must increase the exposure time to get strong diffraction at high angle. You have to make that decision on a crystal by crystal basis. The intensity scale of the diffraction image can be adjusted by sliding the black and white boxes located below the frame. Even at 5 seconds, you can see this crystal diffracts strongly at high angle. Another useful tool is the square button on the toolbar. When this tool is active, you can click and drag a box around a particular spot. Right-click inside the box and choose 3D View. This opens a 3D view window, which allows you to see a 3D profile of the spot. We like to see a nice sharp cone with no shoulders and a circular base. Once the collection has ended, which is 3 sets of 12 images, we're immediately taken to the harvest screen. The spots in the image on the left that have green circles around them are the spots that will be harvested at the given I/sigma value. We want to see many of the spots, especially those at high angle circled. I recommend keeping that value at 5 or greater. Click the Harvest button to begin the process. We're taken back to the Determine Unit Cell home screen, and then we click Index. Usually nothing on the index screen needs to be changed, so just click Index. The software uses 2 default methods to try to determine a unit cell. We'll look at 3 things here. First, the score. Higher is better. Second, the unit cell parameters to make sure they're reasonable. And third, the HKL histograms to give us an idea of how well the data fits the cell. Higher percentages are better. Click the Accept button to select the highlighted cell, and you will be taken to a refinement screen. Click the Refine button once to get an initial refinement. Only 61 out of our 351 spots were used. We want to use more, so move the slider towards More Reflections. Click Refine again. The key metric I look at here is the RMS angle. Less than 0.3 is good, 0.3 to 0.5 is okay, above 0.5 usually means you need to find a better crystal. This one's just above 0.3, click Accept. Next up is Brave. The Brave screen lists the 14 Brave lattices and gives us a chance to select higher symmetry unit cell if it fits the data. Next will be one final refinement. Now that a Brave lattice has been selected, the refinement screen is identical to the previous refinement screen. So use more reflections and refine a few times. The RMS angle is still just above 0.3. One other thing we can do is refine the goniometer zeros by checking the box in the parameters window. Refining the goniometer zeros will help make up for small errors in our crystal centering. Now the RMS angle will drop just below 0.3. Click Accept. Now that we have a unit cell and our crystal seems to be of good quality, it is time to set up a full experiment. Click the Collect tab on the left and then the Calculate Strategy button. The Calculate Strategy window opens and it has loaded our unit cell. We want to confirm the anode is correct and set a target resolution for the calculated strategy. Never calculate to a resolution worse than 0.83. Let's make it 0.7 for this crystal. The symmetry defaults to be chiral. I strongly recommend leaving the symmetry as chiral unless you're absolutely certain it's centrosymmetric. Once the parameters are set, click the Determine Strategy button. I want to change the minimum multiplicity from 1 to 4. Click OK, and the software will calculate a strategy. When the calculation ends, the percent completeness and average multiplicity will be displayed on the lower left. A list of scans along with some timing and data collection information is displayed in the center of the screen. Click Select Scan Parameters next. The Scan Parameters window is where we edit the frame time and frame angle. At GU, we nearly always use 0.5 degree frame angle, and the frame time varies by crystal. This crystal diffracted well at 5 seconds for the unit cell collection, so I'll stick with that time here. Click OK, and now the list of scans shows accurate timing information based on the scan parameters you input. Now that we've calculated the strategy, it's time to import the experiment setup. Click Run Experiment on the left. The blank experiment table is displayed. Click the Append Strategy button on the bottom left to import the scans you just calculated. Add a position line after the last scan to park the goniometer after the experiment. Before starting the data collection, we'll collect a crystal video. Open the instrument doors and turn on the light. Back at the computer, click the Reduce Data tab and the Index Crystal Faces button. Click Acquire New and confirm that the video will be saved in the correct project folder. Clicking Save starts the video collection. The instrument will drive to a preset position and record a 360-degree rotation video of the crystal. Once the video is finished collecting, return to the experiment window to start the data collection. Do not forget to turn off the instrument light and close the doors. Click Validate to ensure all of our scans are valid. And then click Execute to start the experiment. Now that the collection is running, let's return to the crystal video to face index the crystal. To rotate the crystal video, make sure the arrow is inside the video window and use the scroll wheel on the mouse. Each one of these dotted lines popping up is the normal to a potential face of the crystal. The Miller indices of the potential face are displayed when the cursor is on a dotted line. It can sometimes be helpful to increase the max Miller index from 1 to 2. This will allow more dotted lines to pop up. As you can see, we are in control of the solid white line, and our goal is to draw a box the correct size and shape of our crystal by defining the crystal faces. It's important to note that you can only add a face when a dotted line is present. One reason to face index your crystal is to get an accurate crystal size, which is displayed in the bottom right corner. More importantly, indexing the crystal face will allow you to do a much better absorption correction during data processing. The box you draw doesn't have to be perfect, but it should be a realistic representation of the crystal. This crystal was cut from a larger one, so it has an unconventional shape. When you're happy with the box you've drawn, click the Remove Invisible Faces button on the bottom right to get rid of any extraneous faces from the list. Finally, click the Setup tab and Describe Sample button. This is an extremely quick and easy way to input some basic information that will come in handy during data processing. First, the chemical formula should be added. Then the primary color of the crystal, and then the crystal shape. Notice that the crystal dimensions were automatically filled in after the face indexing was complete. To get back to the data collection, click the Collect tab and the Run Experiment button.